Hello everyone, I'm Fei. Today I'm talking about towards reference-free metabolite identification. This is the part one, predicting how molecule will blow up. So first question is here. Sorry, how does this? Wait, why isn't that not working? Oh, I'm just pressed the wrong way. That? Oh, okay, I think. Okay, yes, I think. Yeah, okay, that works. Okay. Everybody's enjoying a pizza, right? So now first question here is nothing about scientific. It's about what's in your pizza. So if this is a culinary questions, the famous British chef Gordon Ramsay will tell you, look, you have a tomato here, some flour, a lot of cheese, and also mixed with waters, and probably according to him, a bunch of Italian sausage and a lot of love. Right?
Pineapple?
Oh yeah, that's a Canadian thing, right? Sorry, I forgot that, Russ. My fault. So, but as a more scientific question here, the biologists and chemists are more interested in more in-depth question here. So, what's going to happen if we put whatever in the pizza under the microscope? And let's go deeper. What can be found when we take those things to the molecular levels? So actually, that's a ongoing question in the last century, and we haven't found all the interesting molecular level answer yet. Okay, so all those things have unknown to us. In the life science community, we call those things a chemical dark matter. So the world we're living are surrounded by the chemical structures. So the food, the drinks you have, the makeup you put on, obviously the drugs you consume, and if you're into smokes and marijuana and all that kind of stuff. All of those things are grouped by molecules. And the molecules going to eventually enter all those very powerful biology systems. For instance, human bodies, bacteria, or just environments. While the top 5 guys and the middle 3 system interact, some magic happens. We call it chemical reactions. It's going to producing a million unknown structures. Those things are being referred to as a chemical dark matter. In the question here is how are we going to find them? I just want to do a quick clarification here. It's not only the structures after reaction we don't really know. They're also including things directly inside your food or your makeups. For instance, a friend of mine did a PhD studies on Italian sausage, just in the next building, the food science. Her thesis was focused on what makes Italian sausage delicious. So to answer this question, in the past 30, 40 years, the most popular sensory techniques from the life science community is using something called a mass spec. So here's a just super high level quick view on what do they do. First, you put the samples here, like in these 3 tubes. Then you put those 3 tubes inside this blue and white blocking machine. Now another magic happens, you got this graph. The graph is essentially have a y-axis called relative intensity, and have x-axis called over that. I'm going to give a detailed example later, but for now, it's just a bunch of numbers. With this number out of that individual samples, you're going to do something called a mass spec search. To do this, the idea is to having a spectral database, a collection of structure and spectral pairs, where you collected over the years. Then you are performing something called spectral matching and ranking. Basically, depending on your choice of ranking methods, you're going to say which one which 2 things are mostly similar. By then you will say, hey, I found my answer. This is what this particular sample is. Is this really true though? the limitation of this particular working flow is actually heavily bottlenecked on this thing. This is based on the assumption everything we already know existing in this bootstrap this blue database. As I just showed like 2 slides ago, there's a lot of things we actually don't know. So now the issue is this is too small. To give a perspective of how small this thing is, so let's look into what we know as until today. So this is a NIST. NIST is American government organizations, but courtesy to them, they are also prepared the standard database, make it public available after you pay them a couple $1,000s. The NIST 23 is the most comprehensive, high quality data set we have so far. It's consisted of 50,000 molecular structures and about 2.4 million structure in there, spectra in there. So depending on the variation of how you're collecting data, each molecule can have multiple spectra. Now let's look at what we want to study. So this is a human metabolomic database, a collection of all the molecules being reported on human systems. By last year, this when the version 6 come out, the particular ones have 260,000 structures in there, and we also have a PubChem, also hosted by the National Institute of Health, the most comprehensive platform to use if you want to searching for the molecular structure. This one is coming with 119 million compounds in there. We can even go further. Now we have this thing called GDB 17. Not everything in here are being confirmed, but that is an outcome from an effort called Chemical Space Project. This particular set consists of everything from what kinds of thing is possible with maximum number of 17 heavy atoms. So put it in perspective, 17 atoms are very, very small. But the size of the data is already 160.4 billion. Then we also have the latest estimation of what we want to look at inside of a chemical space is a 10 to the power of 180s. So now here's a scale of what we already know on the very far left we have 5,000 things, 50,000 things in the dictionary you can looking for, and we want to compare to whichever one of them. So here's the limitations. Now we talk about can machine learning really help with us on this? Well, answer is obviously yes, because otherwise we don't have to talk today, right? So this is still our old working flow, or from whatever the chemistry our chemistry friend want to use. So now, first thing let's do is let's have a compound database. Any one of them we just showed previously. Let's also have a machine learning models able to predict new spectra directly from all those structures. Now, once that step is done, we can simply replace these blue ones and make with a bigger in silico spectra database. The rest of the matching method will be still remaining as is. It will be very simple as a plug and play. Yes. So this is an introduction of why what we want to do and why it's important. Before we're going to jump into the machine learning awesomeness, the next thing I want to talk about is exactly what happens inside that blue and white machine, and why we cause it to blows up. So here's an example. This is our molecular graph. This one is from one. I think this one is from the can't remember the name, but it's a drug using when you have a heart disease. The thing I'm presenting here is called most time referred as a molecular graph. I only show the heavy atoms here because that's honestly interesting. All the hydrogens have been dismissed because it's taking too much space to draw them. The first thing, now this one individual molecules have a journey inside the machines. The first thing what happens is we're going to make this thing have as a vacuum because this guy going to travel in a very high speed. We don't want to slow him down. Next thing we want to do is we want to throw this inside a very powerful electronic field. That's going to put a charge as this orange dot here. This thing become an ion. That means we can steer this thing later with some magnetic and electronic fields. So now this is just a pre-process. That's just the first step. Our friends of molecule friend still traveling in this vacuum space. Now he's meeting with some bad guys. Well, every story have the bad guys. Now the bad guy shows up, grab lightsabers, try to destroy the molecule. One thing I want to mention here is molecular structure actually very strong. To date, we don't really know an efficient way to destroy the atom itself. If we destroy that, we probably can look into either animal world or on the lower end, some kind of thing like nuclear explosion. So only thing we can actually break here, we call chemical bond. It's the connection between two atoms. So now the bad guys decided, hey, he really want to just cut it over here. So he did. So now the bond got destroyed. The molecules we are having now become two parts. We call this thing on the right side, call it a neutral loss because the charge is still on the left side. Why it's called a loss? Because we cannot observe anything inside these instruments without an electron charge. So now this guy's gone. Our friend still keep travel but now he's slightly smaller than his former self. Another bad guy shows up, same story. He wants to cut it again. So he wants to cut again. Now we repeat this process to say that now right side becomes the neutral loss. The right side disappeared. The journey of this very shrinking molecular structures plus this little charge are still going. Now he's reached the end of the tunnel. There are no more better people, no more lightsabers. It means there's something different. A weight scale. A weight scale going to give us the weight of what is remaining of him. Now the scale is okay. Now your weight is 116.3 daltons. Dalton is the measurement of the molecular mass. Then why we call it then? Because you are still carrying one particular charge. So now the new measurement we're using here is called mass over charge. In old days, the very ancient instruments cannot guarantee a single fragment only carry one charge. So that's why this particular term was invented. But in this talk and all the modern fancy $1 million worth instruments, we can safely assume most of the fragments here only have one charge. So you can just think about it this way. Mass over charge is equivalent to the particular mass of these fragments. This is a journey of one single instance and one molecule encountered in that machine. How about we have 100,000 of them? Now we have army of those things entering the same machine. Some of them become nothing happened to them. They never meet a bad guy. Now we have, let's say we have 20,000 of those things remaining. Some of them only met the bad guy once. Now we have 3,000 of that. Then bunch of them are very unlucky. 50,000 of them have been facing the lightsaber twice. Now we have 50,000 of those guys remaining. So for each of the individual one of those groups, we can marry the instrument is going to marry the M over that or the molecular mass of them, and it's also going to marry the how many times we observe that. By doing a normalization over the count of the total count of each one numbers, we can come with this the y value we call the intensities. So the intensity value will be essentially the top peak and the one to the proportion of the highest count. Okay, so this is like a quick example of what happening in the instruments. Let's put that thing into the actual data. This is the mass back out of that structure I just showed you from this specific work I found online. Each one of them, each peak of those are actually coming from different structures. So we have a 326 coming from the bigger one. This is like one step away at 222. And this is the smallest one. Just keep in mind, this one thing I want to show here is there is multiple ways to reaching the same fragments. So for instance, it is possible we can just cut one here and go reach this guy. Then we cut somewhere here, we reach the final step. It's also possible when you can just directly cut it somewhere there, you can reach the same guy. So this is so the way now the way how the molecular structures fragments inside the mass spec instruments is we will call those things a fragmentation graph. The fragmentation graph provided the pathway of how things are how the fragmentation happens. I'm going to talk about we're going to see these things a lot today because that's a central piece of how to modeling this. Okay, so that's just a quick example of journey of molecules and what the mass spec looks like. Now let's talk about all the bad stuff which make those things very hard. Mass errors. So in your high school chemicals class, your teacher might tell you, hey, look, every single element have a particular mass, every single formula have a particular mass. But when you calculated the theoretical mass of our friends, just go passing through the mass spec, I will realize his actual mass is 116.107. But the observer mass on the instruments is saying 116.3. The difference between this thing is called a mass error. This thing is not avoidable. It depends on instrument type, the protocol of people how to processing these things. Is sometimes it also depends on the weather of the day. So just keep in mind, mass error is always existing. Okay. So now we talk about what's the mass spec and how the molecules both are fragments. The question is, we actually machine learning researchers, how are we going to use machine learning models to predict those? Okay, just a quick history license on this, because I do enjoy looking back into all the technology history. Okay, so this is actually a very, very, very old research questions. The first attempt using artificial intelligence to helping predicting mass spec from the molecular structure is from 1960s. It's whopping like 65 years ago. The program itself is called Danjo. It's created by those two gentlemen. Obviously, it doesn't work that well. Then to date, nearly every single method you can think about in the AI literature has been tried on this problem, ranging from expert systems, then also inside the machine learning, so we saw the usage of linear regressions, SVMs, obviously neural nets. We also saw a use. Also aware there is attempted using reinforcement learning on this, which didn't work that well. The latest ones on this also including FlowNet, graph neural nets, and a few other things. The only thing I haven't saw people doing on this particular topic is the fitting data to ChatGPT. That's the only time they haven't been tried. Okay, I'm pretty sure someone tried it. It just doesn't work that well. So as for today, our current understanding for this is given current data availability, a purely machine learning method is still struggling on this particular question. Why this way? Now, question is, why do you think it's so hard to do? Well, the challenge here is to predicting how a molecule will blow up, and we also want to predicting the fragment structure and the formulas. The end user of those tools, also known as our chemistry friend and biology friend, are not unhappy if we only just give them a number. The method of error means directly matching between structural mass and the MOR that is impossible. We cannot just do a giant one-to-one mapping between the possible structures and molecular mass. And one thing I haven't mentioned here, haven't shown previously, is there is something called hydrogen rearrangement. It's a phenomenon where the hydrogen is going to jumping from the ion fragments and to your neutral loss fragments. It's going to totally mess up all your assumption of just cutting in here, everything remain the same. And there are actually existing more complicated rearrangement reactions. We're just going to ignore it here today, because to date, we haven't saw a single method able to model those things. Okay, just quick trip down to the memory lane where we started. So this thing is called the compactive fragment modeling, or somehow we refer to CFM. The project is started by Dr. Felicity Allen, the former student from us. I also extended work a little bit earlier. So the idea with this is to starting from a single input. We're going to analyze this thing first. Then we're going to generating a fragmentation graph, just like the one I showed before. But instead of every single one have an actual measurement on the spectra, this is just a selective possible way to break your molecules. Then in this particular work, to make sure the hydrogen transfer is not going to causing problem, we added this thing called a linear optimization solvers on every single transitions between the parents to their child. This particular linear program solvers are conditioned on the valence rules to make sure if the hydrogen ever transferred, your electron configuration are still correct. So this is just the fragmentation graph itself. Then the few assumptions we made here is first, we assume everything happens in the instrument is a Markov process. That means the fragment happening in the time step 1 is only dependent on happening in step 2. Oh, but it's at 0. Fragment happens in the step 2 is only dependent on the previous steps. So this is actually a little bit confusing graph. I'm aware. I made this thing like 5 years ago when I was young and naive. So each frame here is actually a time step. And every single subset here is indicating the possible fragments you will have on this time step until the end of the time where you're reaching the detector. We put this whole process inside a very complicated PDMs and combined with neural nets and some EM methods. This particular method was a state of art back then. And it does provide a very unique ability to not only predicting the intensity and molecular mass, but also directly output the fragments. Now, let's think like what we didn't do so well of that previous method. Otherwise, we have to claim the victory and we solve the problem. The first of all, this thing is very, very, very slow. Keep in mind this thing is it started before the time we have something called PyTorch or TensorFlow. So everything is handwritten in C++. We have to write the entire backpropagations analyzations ourselves. So yeah, it's very slow. It probably shouldn't be this slow if you're using modern methods, modern libraries. But just keep in perspective, it's about 100 100,000 couriers on CPU-only machines with 300,000 training samples. There is very hard to make any GPU accelerations on this particular problem because we have a latent programming solver and a PGM solvers. And all the assumptions we're making on there are probably not true. The first, the latent programming solver is only giving us one possible solutions in the electron configurations. But in reality, there is probably a couple thousand of them on for every single break. Then this is probably not really a Markov process, but we don't really know. But we made a assumption anyway. The last drawback is at this stage, after we finish the extension of the compactive the CFM project, the data availability become much better. And now we have around 10 times more molecules in the NIST data set and around 100 times more spectra. With some more data, we definitely need to have a better model for this. Introducing something we call the FraGNNet. It's not misspelled, but it does have two N's because we build this thing based on graph neural nets. Actually, two of them. So now our input are still a molecule. First thing is we're still going to generating a fragmentation graph, but this time we're going to do it slightly differently. I will show you in the next slides. Now we're going to have a learn the molecule embeddings from our input structures. Then we're going to combine those two things to produce this thing called fragmentation distributions, where each node here a substructure of your original input, and the color indicating the probabilities of the chance we're going to see it. And by doing that, we're going to hopefully we can get produce a more correct mass spec. Okay, so let's go down this thing step to step. The first thing is how we're going to generate all the fragments. This is our friends. I input the molecule. Now this time I draw all the hydrogen over there. First thing is we're going to convert the molecule become a molecular graph. Oh, whoops, sorry. That's a.
We didn't see the bottom. We didn't see it.
Yeah. Okay. So a molecular graph is essentially a node is representing each element here. Each edge is representing the bond here. We omitted all the hydrogen there because they are not really providing extra information. B, you can always infer how many hydrogen are there based on your valence and the connections.
So each arc has a label being a singular bond.
Yes, so each arc have a label being what kind of bond type it is. So you have a single bond or a double bond. This is actually aromatic, but so in here then we can generating this entire very complicated looking graph. Each node is a graph of itself, where we call it a DAG, because the multiple paths go back to the same graph eventually. So a DAG, for each node on the DAG is modeled by a fragment from the original molecule, and we added a hydrogen tolerance here to allow the hydrogen transfer without actually doing it. I will show the detail of that in the next slides. And for each edge, each edge on here are representing a possible fragmentation pathways. It's basically saying from this node, it's possible to go there by chopping off like those whole things. Okay, so let's take a deeper look. Let's take a in-depth looking of what actually inside each node. So each node is only, just as I said in the previous slides, each node is also have is also coming with a hydrogen tolerance. What does that mean? Well, for every single structures here, it have its original structure or original amount of hydrogen count. as we know, the hydrogen rearrangements reactions could adding more hydrogen in there or remove hydrogen from it. So instead of we physically actually put it into the hydrogen attached to any of the graph, all we're doing is, look, now you can have a extra hydrogen to yourself. Feel free to figure out where it is, but now you can, now this allows this particular node to producing a whole set of extra formulas based on its original formula. For instance, the one we listed in the purple, showing this one can ranging from anywhere from three carbon, 1 oxygen, 1 hydrogen, to 3 carbon, 3 oxygen, 1 oxygen, and 7 hydrogens. And every single one of them have a calculated molecular mass. So therefore, this particular substructures from our original molecules is, in theory, is possible to result in a peak at this range of particular molecular mass from 55.0554 all the way to 61.103. Those things are topologically possible. Doesn't mean you're going to observe that. Whether the probability to say those things will be learned by machine learning method.
Every hydrogen weighs about 1.
Yes, the hydrogen is weighted by 1.007 something. Yes. Okay. So given this new fragmentation graph, the next step we did is to try to formulate the problem in a more probabilistic way. So step one, we define a probability of node distributions, or actually think about it's just probabilities you're going to observe this particular formulas given your parents. Oh, sorry, the probability you can observe this particular node given your parents. Then the second step, given a node of a probability of a node, we define this thing called a node formula distributions. That is, given node, the conditional probabilities of you are observing any of those formulas at this particular node. So in here, we have a base formula of 3 carbon, 1 oxygen, and 3 hydrogens. We're going to put a 5 different variation of it. Then for each one of them, we assign a probability values to it. That's our node formula distributions. Then to calculate the actual formula distributions from the beginning of the everything, is essentially a summation of those conditional probabilities. For instance, at node 1, we can generate all 5 different formulas, and then each formula is going to point to one of those formula on the right side. One thing you may notice here is there is a single edge jumping from the node 3 back to the formula 3, because it is possible. Okay, it's not even possible. It's very common for molecular structures to have the same formulas. For same formulas. So that's why this is the probability of the same formula 3 is actually a summation of the probabilities on this block and that block. And that block together. Oh, now we define two probability distributions here. Now the last probability distribution we want to define is we call the mass distributions. Because as I mentioned, there is this thing called mass errors. There is also the challenge of multiple formulas going to have a very, very close molecular mass. They want to be distinguishable on the instruments. So the similar formulation method is given a particular formula, given a particular molecular mass. The chance of seeing this particular mass is actually equal to the summation of these conditional probability distributions. To take into account of the observed mass and theoretical mass, because there will be a small gap between them, we use a narrow Gaussian distribution mask on top of it. So for instance, this is a very narrow Gaussian distributions. if the M3 and M6 are all in them, we're just going to using this form to dictating which percentage it is on each side. So now let's put everything together. So therefore, we in the FraGNNet, we model the mass spec as a distribution over molecular mass, the P of M. The PFM is conditioned on the probability of every single formulas we're going to observe. It's also actually depend on the input structure. And PFM in this case only depend on the original molecules. So just by doing that, we get rid of the Markov assumptions. We only condition on the input and observations. And every single part of these things can be parameterized by a neural net. Since this is a probabilistic formulations, we can just learn the whole thing through a negative log likelihood. Okay, so that's just a formulation, probabilities, and equations. How they actually do that in the neural nets? Because we just generated like for every single one of them, we effectively generating a couple thousand to tens of thousands different structures. So so first, we still have our molecular graph. Then let's generating that particular fragmentation graph itself. Each node of them are actually going to representing at what's called a fragmentation node masks. Because think about it this way, each of your fragments have to be part of your original structures. Well, you can just simply put a 0 and a 1 on top of that to preventing your neural nets to looking into original feature representations. So given those two things, we introduce something called molecular embedders. It's just a standard graph neural nets. You are taking into account of your the input will be the molecular graph, then of your original structures and your node mask. So by combining the molecular graph and the node mask, it's a very efficient way to creating the fragment input for the neural nets. Then the second step is we are putting into this thing called fragmentation graph embedded. Because this thing is actually a second graph. If we already have the one graph neural nets, why not just having two, right? So this is the second graph neural nets where input, where the node is essentially one of them multiplied by the infrastructure. So the second graph neural nets, on the second graph neural nets, we are doing a node level output. We put a node level multilayer perspectrons for each individual node, where each individual node going to output the probabilities of this particular formula. By aggregating the predicted values of the formulas, we can assign them become the predicted spectra. So for instance, those two things on the right side are all coming from the same fragmentation node. They just from different formula itself, and two of them can also aggregate into the same peak because they have the same molecular mass.
People know what post structure?
I
don't.
I mean, it's high school chemistry, right? I thought everybody know it, right? Yes. Okay. So this is how we model these things with just two graph neural nets. Let's see how if this thing actually works, right? This was trained on NIS20, a slightly older version than NIS23. We're using only one type of spectra because actually they have multiple different variation that. So to simplify, to make things simple, we're just going to use this one specific type, like the M plus H ADAC type on the obtrap only. the spectra is merged to save time, which I know every single one from my chemistry friends. I hate me doing that, but hey, this is machine learning. So by merging that things, it can make the training much faster because it's just proof of concept. So overall, there is around 13,000 merged spectra for training, and 4,000 of them are reserved for evaluations. So we are doing a 60-40. We are doing a 60-40 distributions. For distribution on this particular setup. The model size is surprisingly small by today's standard. It's only 1.7 million parameters. I think, yeah, because those days, if you want to do anything big, this thing has to be a B, right? The training spectra can be done in one single 840 GPUs around 12 hours. The very interesting fact of this, the limitation on this is not actually not actually how many parameters we have. It's because we generate way too many spectra in the substructure on there. We cannot fit all the things into GPU memory efficiently. So let's first look at a predicted examples first. This is the actual real example. I can't remember what the structure it is. I randomly picked one from our testing set, and this is our predicted ones. We call this a mirror plot. The green ones are the real ones. The red ones are predicted ones. As I mentioned before, since we are directly predicting the probability to observe the individual fragments, we actually have ability to tell which structure it is by predicting, rather than just only give them a magic number, which every single chemistry hits. So in this case, the formula one, which is here, the highest ones, the model thing is actually coming, most likely is coming from these individual structures from the original ones. There is a very, very low chance is coming from those two guys. Then one thing is very cool is in the peak number 4, the formula 4, the model is able to learn all those 3 guys are contributed equally to that particular peak, because essentially they are if you remove those things from the molecular structure, they are exactly the same underlying graph structures themselves. But when attached back to the original molecules, they are slightly different.
They don't have to one.
Yes, because there is more things on the left, so just kind of show them. Okay, normally we will say, hey, normally say, hey, we're going to do some kind of evaluations here, right? Okay, okay, sorry, we just showed a predicted example, so now we're going to show some kind of a more meaningful measurement of the performance. Now, first, we do what every machine learning researcher most likely to do. Let's say they do a random data split, toss a coin, random split your data, and let's see what's going on. So, so here is a quick comparison between our model and our close competitors. This one is done from by Sam Goldman from MIT 2 years ago. So we showed 2 different ways when you try to measuring if 2 peaks are essentially a pair. The first one is measured just by the 10 ppms. If the molecular mass are within the 10 ppm Dalton difference, they are considered a pair. The second ones are measured by essentially put every single peaks inside a bin. So for instance, for 0.01 Daltons, your bin size is from 0 to 1,000. We are looking at 0 to 0.1 is a bin, and 0.01 to 0.2 is another bin. So the second one is a little bit easier, and the first one is slightly harder. But the first one is more realistic. So the common measurement in this space is called cosine similarities. I think everybody can know what cosine similarity is in this audience. So our method, the FraGNNet, is doing quite a bit better inside of this particular testing than our competitors, the iceberg. So they were doing about 0.4 in terms of cosine similarities on 10 ppm, and less so on the binned ones, because the binned ones are actually easier. Because then we also compared this into some just giant neural net approach. The first one is called MassFormer. It's actually from the co-author on this project. That is a giant graph transformer, probably 20 times larger in terms of number of parameters than the FraGNNet. It cannot really do the 10 ppm because it's not really predicting the very in-depth, very high resolution data. But even only measuring on the binned versions, and their performance are not as good as what we have. We almost have like a 0.9 difference over there. We also tried one with something called names. Okay, this is not actual names. This is a modified version of names. Names was published from Google a couple years back. Can't remember, but yeah, by the way, the names also is super cool. She had a paper on how every single molecule can smells like the artificial intelligence on perfume making. So that is super cool. Check it out. So anyway, so this is a modification from names. We made that thing 100 times more capable in the higher resolution, because names was designed only to predict everything to integer accuracy. We show that while names is also not very good. Oh, the ultimate question here is okay. Sorry. This is only to show how similar your predicted spectra is. As my supervisor always say, nobody cares about that because it's only pretty numbers. Well, I do great because the goal of this is actually to say, hey, how many things you can retrieve? How many times by using your predict spectra, you can successfully grab the actual compounds from in the real problem. This is a test we conducted using our holdout data set, where the retrieval candidates are from the PubChem, the 119 million ginormous database of molecules. We grab them. We select everyone. Select candidates from the 10 with a 10 ppm mass tolerance, because outside of the 10 ppm mass tolerance is not going to match anyway. To save times, this one is conducted on using 49 structurally closed candidates determined by ECPY for fingerprints. So that's just a way to measuring whether two molecular structures are close enough. It's not perfect, but that's a common method in bioinformatics. As we show here, on this particular setting, we call it MS2C, mass spec 2 compounds. Our method is doing like 3% better compared to iceberg in terms of top one. Then about like 2-3% better on top 10 as well. But
your tool basically just finds a ranked order.
Yes. Yeah. By now we will say, hey, our stuff is better, right? Until we met this guy, Professor Sebastian Baker, a very famous figure in this particular area. He's from Germany, and he always making some very funny comments. And this is not his comments. This is actually the title of the paper he put on bioRxiv. The paper itself has been published a month ago in Nature Communications. And he changed the title, just be clean. But this is exactly what he said. Small molecule machine learnings, all models are wrong. Some may not even be useful. What does this mean, right? It's actually because most of machine learning models here we're using, just like I showed 2 slides ago, I rely on random split. The way you just toss a coin, you say data point to go to this training, now data go to testing. It's actually have quite a bunch of limitations in this particular, well, in the setup in this context. So machine learning in small molecule works on the assumption of that small molecule, the similar molecule is going to have the similar properties. And by doing random split, we actually introducing structural bias where the similar structures can end up in either on the training set or the testing set. And it is also leading to the problem where it's very easy to overfitting. The model will be performing super well when you're doing random split, but when they actually deploy this into the case where say, hey, let's actually go use your model to hunting new molecules. That's going to fail spectacularly. We observe this in time over time. It's also bringing the concern of generalizations. Is the random split does not challenge the model to generalize to true novel structures. And the novel structures is the one they probably going to win the Nobel Prize of. So that's actually, there is a big force driven from another side of this, another side of a scientific company say, hey, you need to do more on not a random split. So this is an example of why random split is going to cause a problem. This is an example where you can say the difference between top structure and bottom structures, almost like you can say it, right? Yeah. So the difference is only because the top ones have one more extra carbon chain here, and the bottom one have a less one. The rest of the things are exactly the same. Then, especially in the mass spec, where there is a chance of a fragment become a neutral loss, you're never going to observe it. Just like in this case, you're going to have a nearly identical spectra. So if the model able to learn this thing in the training set, it doesn't have to do anything. Okay, it has to do very little work on the generalizations. All it have to do is let's memorize what this guy looks like, give the answer. So to better access how our model works in this setup, we introduced, well, not we, yeah, it's still we introduced. We're actually collaborating with Sebastian Baker. Okay, we introduced this thing called maximum common substructure separations. Those are three examples of the maximum common substructures, A and B. Those are the common substructures. Those are that. We try to enforce the model or enforce the distribution such that most similar stuff going to training set, similar stuff going to testing set, and testing set and training set will be as different as possible. This is also a measurement on the grain to show how different things are in our testing set, in this new testing set. So the lower number is the less similar. The red sample is actually similar. So this is the red ones is actually our random training set. Let's talk about the performance measures. Since I only have 5 minutes. So this is our performance on the MCS split. Everybody get a giant performance hit because it's very hard. Also, only measured by the binned ones. We are only the FraGNNet itself only doing 0.52, down from 0.71 from the random set, and the precursor iron only, which is just like reporting the molecular mass directly without any machine learning, is able to do 0.15. One thing is very striking is in this particular setup, our famous graph neural nets is only able to do 0.119. It's literally just worse than random guess. Then if you do feed-forward neural nets as NIMP doing, it's doing actually slightly better because it have a less chance of overfitting. The retrieval test in itself, actually a very surprise to us too. The FraGNNet is actually doing a very decent job. Have a 46.6% top one hit, compared to our baseline model have less than 1% accuracy in the top. That's how hard the testing set is. Okay. So just one thing I want to mention here in this same test evaluations, we also tried a reverse mass spec to small string transformers. That one have 0% top accuracy. So that's how hard the particular problem is. Okay, so in conclusion, the FraGNNet is a known method for mass spec predictions with principled probabilistic modeling. It had self-performance on the spectral predictions and the compound retrieval testing. It meet the key requirement of area of resolution, scalabilities, and interpretabilities, and it's doing super well in the out-distribution analyzations. Okay, yes. Normally I will say, hey, this thank you, but this is just a little bit of the teaser here. In my titles, I said this is part one. And this is the graph I showed you a couple, I said 40 slides back on this working flow of things. Now we replace this thing with in silico ones, right? We still have a predicted in this way, and we're still using an existing compound database. As I mentioned, there is 10 to the 108 power of 180 different molecules we haven't even seen before. So what about we are replacing this thing with another machine learning models? So we're probably going to be able to share more details of what we did for this in coming weeks. Once we finish that 40-page long response letters. And thank you. And